Namaste. Hope you are doing well. Today we will tackle the seventh problem of ISI MSTAT 2023 PSB. And yes, the problem screams design of experiments at you. We have to allocate land meaningfully for Mr. X so that he can do a good comparison of 5 different varieties of wheat. So the first part is allocation of land, and second part is first part is the allocation of wheat varieties to the given land, and the second part is once that allocation is done, how would you do a meaningful statistical analysis? So let's get started. Now, even before connecting some dots, we have to build some intuition about this visual image given to us. And naturally, some questions that can come to mind are, how would the distance of any plot, say this, from the natural resources around it affect the quality of the plot? And second, because it's statistics exam questions, how do we encapsulate that information by some math? Now, it's quite intuitive, right? If this plot is closer to the mountains and the river, then naturally mountains and rivers should have a greater effect on it compared to forest and lake. Similarly, for this plot, the effect of lake would be quite prominent, forest also a little prominent, but river and mountains perhaps not so much. So we have this intuition about the geography and it makes complete sense. How do you express it with some math? We do it like this. We have to have an indexing structure for the entire grid of 25, which we can have through these variables I and j. Notice that even it's 0 to 4, essentially it's a 5 cross 5 grid. I can take 5 values, j can take 5 values. Now notice, say this plot, I is 0 for this and j is 0 for this. And if you substitute I and j in this expression, you get m minus L plus R minus F, which makes sense. M and R are positive, indicating that mountains and rivers have a good enough impact on this plot, whereas forest and lake do not so much. And similarly, this indexing can give meaningful effect of natural resources for all the plots. And there's a reason why this indexing, because we'll see later, we could have had an indexing which could have just eliminated L and F altogether, but there's a subtle nuance to it that would come. Now we connect the dots. The way that we have this map, we see heterogeneity coming from two directions. North to south because of mountains and lake, and east to west because of rivers and forest. So essentially in this indexing, I and j, they can be attributed to this heterogeneity, right? East to west is I, the variable I, and north to south can be attributed to variable j. Even this is going to come later. And our interest is not the natural resources. Our interest is to compare the wheat varieties. So now that we have these two connecting points, which design of experiment would we use? Perhaps you have guessed it by now. It's going to be Latin square design. And it's going to be Latin square design because of its speciality of eliminating heterogeneity, which we actually want to do. We first of all don't know how the mountains, forests, lake and river are going to affect, and we also secondly want to sort of cancel out that effect in our later on statistical analysis. So for Latin square design, this is how the allocation would work. Each of the 5 varieties would have 5 crops each, so 5 into 5 is 25. Now for variety 1, arrange the 5 crops in such a way, say something like this, that each row and each column has only one crop of type 1, and similarly fill out the remaining grid accordingly with this. And the assumptions which are also associated with Latin square design are that these effects of natural resources, when we do the statistical analysis, would add up to zero. And even the effects of different crop varieties, when mathematically expressed, would add up to zero. Now, this is a decent enough allocation. We move on to part B. We have to build some intuition for this as well, or connect some dots, whatever you'd like to call. We have the allocation, which distribution we would want to use, sort of attribute that distribution to the yield from crops. That would be helpful for analysis. And yeah, maybe you have also guessed it, it's going to be normal distribution. So if yijk, y subscript ijk is denoting the yield in the ijth grid point with the kth crop in it, then we would have it follow a normal distribution. Notice that this sigma square being the same for all means there is homogeneity in variance. And Ri is the component coming from I over here, this one. And similarly, Cj is this component. So we have Ri and Cj coming from I and J. And Tk is the effect from the kth crop variety itself. And just normal distribution is not enough. We have to look at specific distributions coming out from the various possibilities from this, because we have 25 of such random variables. We want to cut down to what we really need. And yeah, if you are familiar with the way design of experiments works, this is what is the next step. We would have this as the variation coming from the treatments, which in this case are the crop varieties. And this would be, you can see, it's like eliminating the other things, the errors, so to speak. An interesting thing about this is the grid itself. Notice that it seems like initially it could just be represented by I and J. I goes from 0 to 4, J goes from 0 to 4. That's it. But we also, for the math to be proper, we also want K to come up somehow. And that's how we sort of convert this two-dimensional grid into a three-dimensional indexing, where K is sort of dependent on Ij. So I and J can take values from 0 to 4. And when they have taken values from 0 to 4, then K would be that crop variety, that number of crop varieties, say crop 0 or crop 1, that would be in the ijth plot. So if I have something like y 1, 2, 3, it means this position would have the third variety of crop. That's what it means by this indexing. And yeah, there are a lot of notations which we have to make sense of. This is the grand mean. Notice even in the indexing, we have the summation from I and J, and K as an index is dependent on Ij. So we can also write K as K subscript Ij. This is the grand mean of all the 25 random variables. This is the mean for the ith row. This is the mean for the jth column. And this is the mean for the kth variety. Hence, when you look at this makes sense, as this is the variation coming from the variety of crops or our treatment. And this is sort of eliminating everything else, right? So this is the error, so to speak. The error coming from the rows, the error coming from the columns, the variation from rows, variation from columns, variation from treatment. If you remove them, then what remains is your error variation. And these two things are useful for us to get the answer of how we would do the comparison. So our hypothesis of interest is going to be checking whether all the treatment effects are the same. And the alternate is not this, which means there are at least two treatment effects that differ. And the way we have to compute the statistic, you may know it's going to be a F distribution, but how so? We would have to have the degree of freedom associated with the error sum of squares. And it is quite intuitive. You have like 25 of such observations and one grand mean. So that's 25 minus 1. You have 5 rows and one grand mean, so 5 minus 1. 5 columns, one grand mean, 5 minus 1. 5 varieties and one grand mean, 5 minus 1. So this structure intuitively gives you information about the degrees of freedom that you can have. And it's this. Similarly, for SST, we have 5 treatments and one grand mean. So yeah, there are 4 degrees of freedom that we can have. Now, the statistic of F distribution is like this. And just for further insight, this can be broken into this summation on the numerator. And how we proceed then to convert it actually to a F statistic is divide the numerator and denominator by sigma square. We can do that. And we take the 5 over here. Because this is a mean and this is a grand mean. So the variance associated would be scaled appropriately by 5. And that's why this structure is essential of the numerator. And this structure on the denominator, because we have the normal observations as it is in the denominator. Now, we have the statistic which follows this distribution. And simple, we reject the null hypothesis of equality if the cutoff value for the appropriate distribution at level alpha is exceeded by the observed value. And if it is rejected, there's something more to be done. That is multiple tests. Now, assuming your F statistic leads you to the rejection of this null hypothesis, then your problem is not solved. Because had null hypothesis been accepted, done and dusted, you would just report to Mr. X that all the varieties are giving the same yield. But because that's not happening, then Mr. X would ask you, okay, if all varieties are not same, then which varieties are of more importance? And that is where the concept of pairwise tests comes in. We can have 20 pairwise tests. Each pairwise test would take up 2 varieties. That's why the null hypothesis would be both their effects are going to be the same, and alternate would be effect of the first is going to be greater than effect of the second. So that's why 20. Because if you think about it, there are just 10 ways to choose 2 varieties from 5. But here ordering also matters according to the null. That's why it's 5 permutation of 2, which is 20. And we would be rejecting the null hypothesis of equality in this pairwise setting at level alpha star. Alpha star could be alpha, or if you want to be more conservative, you could use something like Bonferroni correction, in which alpha star is lesser than alpha to account for probably more likely rejection of null hypothesis. Sometimes we want to control that, so that's why we use a smaller alpha star. And this is the T distribution statistic, which under H naught EI is going to follow T distribution. We have the pairwise mean difference in the numerator and the scaled pooled sample variance, standard deviation, I mean. Its structure is like this. And what you see over here is this pooled variance is using these 2 variances. And what is the structure? It's this. So for a given variety of crop, the variation coming from that variety, that is actually captured over here. And in this hypothesis testing, we have 2 varieties. So we have 2 variations And that's sort of incorporated into the pooled variance, which gets appropriately in the formula to the T distribution with this degrees of freedom. And if that is greater than the cutoff, then we would say that variety T1, has a greater yield than variety T2. And that's it. You're done. And some ways to build your base for exams is that in this question, initially there were these seemingly complicated geographical structures of the mountains, rivers, lakes, and forests, whatnot. But those are not of our interest. So similarly, in questions, when there is various factors that are in all four directions, then we should try to learn the art of eliminating the irrelevant ones and look for structures that do that elimination, because we only want to be concerned with what we want to be concerned with. That's it. If this was helpful, then the request is to identify and allocate resources properly, which would be yielding better productivity for your work. One such resource for you is time. So, yeah, take care. Hare Krishna.